let's see. Go to a full slideshow. Okay. Let me know if you cannot see my slides.
It's good. It's good.
Okay. Great. So this talk is a little different from some of the previous excellent talks that you've seen. This talk, I guess I'll start with a little apology. The apology is that this talk is actually not very much about machine learning specifically. What I'm going to talk about is two things. I'm going to talk about a paper that I wrote that does a lot of text analysis. And then I'm going to talk, I think, more broadly, zooming out a little bit about how you might use text analysis or use text as a source of data in your own empirics. And I think that part will contribute a little bit towards thinking about, one version of the empirics that you might run with text data could be machine learning models. So I'll sort of nod to machine learning a couple times in the talk, but for the most part, you should think about this as like a discussion of an input that you might use in these models. And so, yeah, that's why this is the one talk in the webinar series that does not start with sort of machine learning. And so apologies for that. But I'm hoping that you'll find this sort of interesting and potentially useful as you think about sources of data when you run the kind of predictive models we've been talking about. And when you think about running other maybe more causally focused models, or potentially at the same time. So I'll start with the paper, and then I'll zoom out. So this paper, I guess one more apology. This paper is published, which is, I know, kind of outside the norm for what one usually presents, but it is the one of the papers that I've worked on. I think it's the one that sort of provides the clearest view into the text analysis process, and some sort of useful suggestions along the way for dealing with a lot of data all at once, a lot of text data in a paper. So that paper is Temperature and Temperament, Evidence from Twitter. And I'm an environmental economist, so I'll start this talk by showing you a graph of what we sort of think temperatures are going to look like over the next century or so under different versions of climate change. So on the left side of the screen, this figure is not mine. This comes from the most recent summary of the IPCC reports. And what you see here is the historical data in gray, and then various projections of temperature change on the right in different colors. And you can think of these projections as being from least severe in blue. So that's RCP 2.6. These are just what are called representative concentration pathways. They're projections both of population and of emissions growth of what the world might look like. And if you feed in a more, I think pessimistic is the right word, a more pessimistic scenario, like RCP 8.5, you get quite a bit of temperature rise. And so 4 degrees Celsius change is pretty dramatic and devastating to a lot of aspects of both human and animal and ecological life on Earth. So that's where we start. The idea is that we want, in papers like this one and the many papers in the climate impacts literature, we want to understand the implications of being on this lower pathway versus being on this higher pathway. And that has a lot to do with what kind of emissions we produce over the next 80 or so years. The right-hand side of the figure shows this disaggregated geographically across a portion of the globe. And the observation that I want you to take away from this is that this is not a homogeneous change. So climate change is not simply an increase in temperature. I think that can be obscured by a lot of the rhetoric, but it's a heterogeneous change in temperature as well as massive changes in weather more broadly. So precipitation changes, snowfall changes, many other changes. And understanding how these different changes in different parts of the world might affect different populations is really important. And that's what this paper does. So the question that this paper wants to answer is, how can we credibly measure people's preferences for ambient temperature? That's important in a climate context because we're essentially shifting we're shifting the distribution of weather that people are going to experience. People have preferences over weather. That represents a welfare change. And we think probably a welfare loss, but we need to estimate people's preferences for weather or for climate in order to understand that. So this gets to a really fundamental problem in environmental economics and in other fields of economics, which is how do we measure the value of non-market goods? So non-market goods often means public goods. So for example, beekeeping or education or vaccination, these are sort of public goods. These are things that we like, but that we don't always fully internalize the benefits from, and so we tend to underprovide them. But there are also non-market goods that are actually not good, that we would prefer to avoid. Maybe non-market bads is a better term, or public bads. Examples of this, besides weather, are air pollution, noise, traffic congestion. The tricky part about these goods is that we don't have direct markets for most of them. So we can't buy and sell air pollution in a market. We can't buy and sell vaccination in sort of a public goods sense. And we can't really buy and sell ambient temperature. So being able to estimate preferences for these requires a range of techniques that sort of lie outside the usual scope of demand estimation. Traditionally speaking, at least in this field, the prevalent approaches have been either indirect market approaches or direct elicitation. Indirect markets just means like hedonics most typically, and that's the set of papers that I'm going to speak mostly to, or that I sort of build on in this work, but also defensive expenditure models, travel cost models, and there are others. Direct elicitation is more like survey-based approaches, so you can think about contingent valuation, basically directly asking people about their preferences for the provision of some public good, maybe how much they're willing to pay for that provision. The strengths and weaknesses of these approaches vary. These approaches vary quite a bit, but one of the central challenges in many of them is either we don't have enough data, or we are unable to, for some reason, to control for unobservable cross-sectional variation. So to be more precise about this in the climate sense, these hedonic models tend to compare property values in different parts of the country, of countries or in the world that also experience different climates. And so the idea here is that if I'm living in California and I'm paying a certain amount of rent, getting a certain amount in wages, and I can net all that out, what remains is sort of the amenity value of just being in California. And what these models try to do is they try to kind of pick apart those pieces of that of amenity value. So they try to pick apart the value of being near the coast. They try to pick apart the value of whatever air quality is being experienced in the area where this person is living. And they try to like pick out the value of the weather. And we tend to do this in a linear regression, or a model similar to a linear regression. And that has a lot of value and a lot of benefits, and I think these papers are really important, and I'm not saying that we shouldn't be writing them, but often just by the nature of the model, we have to identify this preference for climate off of cross-sectional variation in climate. And so that introduces all of the concerns about correlated cross-sectional variation that are typical. An alternative might be, and an alternative that I'm going to propose to undertake here is to infer preferences from changes in people's emotional state in response to different levels of the good, in this case, different temperatures. So does that alternative make any sense? Like, what are we even inferring preferences from here? Well, I want to try to justify this by starting with this observation. Many of the non-market goods that we're thinking about, weather, of course, but also air pollution, noise, others, are experienced simultaneously by many people all at once. So if we were able to look at how people respond to these changes, we might be able to map out some sort of experience utility. So the idea here is that emotional responses to a change in situation, whether that's increases in air pollution, decreases in noise, changes in weather, those represent a kind of experience utility, or a change in experience utility. And this actually follows a very long tradition in economics and psychology that dates, most recently, I guess, in terms of theory, back to Kahneman's thinking. The paper I cite there is one of the first ones I've seen to talk about what experience utility. But it really goes back to Bentham's writing in the 1700s, where he talked about, utility as a measure of sort of pleasure minus pain. So this is an old idea in economics, but it's being updated. It's being updated here to think about a data source that might actually be useful for helping us understand preferences as we now think about them. So the approach is, with sufficiently frequent observations of emotional state, with a nice panel, we can leverage as good as random variation in the non-market good, so here weather, to estimate preferences for weather. Specifically, in this paper, I'm going to be measuring emotional state with kind of a proxy for that, that measures the emotional content of text on social media. So I'll be measuring emotional state using sentiment analysis, which is a natural language processing technique, also known as opinion mining. And the underlying idea here is that the word choice that people select when they craft the text, when they speak, when they post on Twitter, some of those word choices can actually indicate the underlying emotional content of the person. So what am I doing today? I'm going to be using the responsive online sentiment and as good as random variation in weather to infer preferences for climate. Okay. So how do we do this? How do we do this in the data? Well, in order to get a sort of massive data set on expressed sentiment online, I turn to Twitter. The Twitter, I presume you all know this more or less, but Twitter is a social networking service. It was founded more than 10 years ago. And this is probably dated, but according to marketing materials from 2017 or so, they have 300 million active users, 500 million in the US. Tweets are, again, this is dated as well, tweets are limited to 140 or 280 characters. They're basically public status updates. And what I do to collect these data is I collect more than 1 billion geolocated tweets from the US between 2014 and 2016. So geolocated in this context means I can locate these tweets more or less down to the, not the precise location where they occur, but down pretty close. So maybe like a neighborhood. You can think about a neighborhood in a city. That's roughly the level of granularity that I'm going to be able to work with. What I actually do econometrically is I am going to compute express sentiment with some algorithms that I'm going to talk about, and then take metro area day averages. So whatever coarseness I have in location is going to be absorbed up to the metro area. Very little concern about misplacing tweets at that level. And then I'm going to take an average over the day. And then I'm going to see how that compares to changes in weather. Okay. So to pre-process the data, one of the steps that we'll talk about a little bit more towards the end of the talk, but one of the main steps that you need to do when using text data is you need to sort of clean it or pre-process it first. To pre-process the data in this context, I'm going to remove punctuation, I'm going to remove URLs, I'm going to remove hashtags, mentions, and I'm also going to remove weather-related tweets. And that's important because on my right-hand side, I have weather. So if I have somebody saying, oh, it's really hot today, or some word like that, what I'm going to be picking up there is maybe sort of a conscious effect of weather. And I go into this in another paper in more detail. But the idea here is that we really want to focus on the subconscious effect of weather. So I want to be thinking about somebody talking about their favorite football team, or what their friend is doing today. And I want to see how that emotional state varies in response to the weather, whenever they're talking about something else that's not specifically weather. For the record, when I estimate this with weather tweets only, I get a much sort of stronger, more pronounced response, as you might expect. There are, gosh, I think when I looked it up, there were 50, maybe 100 sentiment analysis algorithms available like 3 or 4 years ago, which at this point, I'm sure it's like 200 or 300. There are a vast array of ways to compute emotional state from text. I'm going to use a subset of those, and I'm going to use a subset that I think is both most appropriate to the setting, which is online status updates, but also a couple that are sort of more grounded in traditional research on translating emotional state from text. So I've listed out some, or the sentiment analysis algorithms that I've used in this paper. A fin, I'll just give you kind of a high level on most of these. A fin is designed for social media. It's actually built on an older lexicographic dictionary that wasn't designed for social media, but this one has been updated. Hedonimeter, you might have seen some hedonimeter related papers. These are like the happiness guys out of UVM. This is Dodds and Danforth. Basically, this is a large list of crowdsourced words that have positive or negative valence, and I'll talk about what that means in a second. Luke, LIWC, this comes out of the University of Texas, and this is one that's actually grounded in a series of psychological studies where they ask people to describe their emotional state after writing a piece of text, and then they extracted the words that correlated to that state. Vader is the one I focus on in the paper for most of the additional checks. Vader is really a nice sentiment analysis algorithm, particularly for online text. It does an excellent job dealing with some of the nuances of negations and some of the trickiness of actually analyzing sentiment. And then finally, I have two others. So profanity is in the paper. So profanity is kind of what you expect. Profanity is just a measure of the degree to which people use profanity or don't use profanity in their tweets. And finally, I'll talk about, maybe I'll talk now about this emoticon train measure that I used that's not actually in the published paper. It was in an earlier version of the paper. And so just to give you kind of a high level on how these work, I'll go to one of these. So the idea here is that for a fin at least, and this is true for most of the measures that I use, a fin is what's called an expert created dictionary. So these are people who study the use of text to obtain emotional state. And it maps around 2,500 words to what they call valence scores. So valence is a term that comes out of the psychometric literature. And the idea is that it measures sort of the strength of emotional response. So in this particular metric, you can have scores as low as -5 and as high as 5. So 5 would be a very positive word. -5 would be a very negative word. This metric was built specifically for assessing Twitter data, so it's appropriate to my setting. And they employ what they call a lexical affinity procedure. I would just call this a dictionary approach. They're basically the same thing. The idea here is, like I said, you clean the tweet of punctuation, URLs, whatever nonsense you want to take out, and then you tokenize this tweet into words. So tokenizing just means you're separating this block of text into separate words. Okay? You drop if the tweet contains stop words. So in this case, negations. That means, rather than saying, I love ice cream, you might say, oh, I don't hate this ice cream. But a naive approach would say, oh, I see the word hate. That's a negative word. This is a negative tweet. This is a little more nuanced in that it sees the word don't, and it says, ooh, there's a negation here. This is probably too complex for me to deal with. I'm going to throw it out. Similarly, for the reasons I said earlier, it drops weather tweets as well. And then all it is a simple mean of the words that actually match into a valence score. So just to give you two examples of this, the tweet "Happy Anniversary, Mom and Dad" would generate a score of 3, simply because happy has a score of 3. So anniversary, mom, and dad, all of these are non-scored words. And that's important because a lot of words end up being not scored in these metrics. And that's, I think, kind of fine. The second tweet that it would code, or second example tweet to think about, is I can't watch Matt cry. Again, only one word is actually scored here. It's cry, and it's sort of a slightly negative word. So this tweet gets a -1. So most of the approaches are basically along these lines. The only difference here, and the only one I think maybe we're spending a little bit more time on, is the ML measure. So this is what I call the one-pointed train model. It's just a machine learning approach. The idea is it's a very basic projection exercise. So we start with our labeled data. That's just tweets with emoticons. Again, at the time of this writing, this tells you how quickly things change. The Twitter platform had just started supporting emoji, and the Twitter zeitgeist had not like shifted en masse towards emoji, or the online zeitgeist. So emoticons were what I use as the source of labels. You could do this just as well with emoji, although it might be a more complex mapping. Anyway, the training data is created with these tweets that actually have emoticons, and I use that to train a multinomial naive Bayes model. So this is actually a really simple lexical model, but it actually works quite well for text classification. I classify the full set of tweets using this. So having trained the algorithm, I classify the full set of tweets. I'm not the first person to come up with this idea for rating text, and this actually achieves 80% classification accuracy according to Wilson, Viva, and Hoffman. Obviously, they did this on non-Twitter data because Twitter didn't exist when they wrote the paper. But since this is kind of a pure classification exercise, I'm just going to code it as binary, and it'll either be 1 if it's positive and 0 if it's negative. I throw the example sentences into the model and get what I hope to get, which is that happy anniversary, mom and dad is positive. I can't watch Matt cry, which incidentally would also be a source of labeled data, as a 0. Good question from Juri. Good questions from Juri. Juri asked, did you use a public or a private API to download the tweets? I used the public streaming API. So I had and have a computer that has been ingesting tweets from Twitter, public status updates from Twitter for the last 5+ years. That is, in my view, the best way to get a huge bulk of tweets, especially geolocated tweets. I have not typically dealt with misspellings. So you can do something called stemming, which I'll talk about later, which would deal with some misspellings. But if somebody used a word that would otherwise be coded with some valence, but it was misspelled, then it just wouldn't get coded. And that kind of all falls into the noise. And there is a lot of noise in these models, right? There's a lot of noise in text data, and a lot of what ends up in the error term is just maybe this kind of miscoding, maybe slang language. And I guess the question here is whether that generates systematic bias in your research program. Okay.
Patrick. Hi, Patrick.
Hey.
After Yuri's question, also there is another question in the question and answer section.
Oh yeah, let me pull that. I'm having a little trouble seeing that with my screen maximized.
Do you want me to read, or?
Yeah, please.
How do you dismantle the emotional response to weather from emotional response to someone else's tweet? What if I am tweeting because I saw someone complaining about weather? Hurt behavioral versus genuine individual opinion.
Right. Yeah, it's in a loose sense, it's a general equilibrium question. And one way to respond is to say, I guess the right response is to say I run a robustness check where I look at people actually mentioning others. So this isn't going to capture all of this kind of spillover, but it is going to capture quite a lot of it. And I don't see a change in the point estimates based off of that. So if that kind of contagion is like generating some sort of spillover violation, it doesn't seem to be biasing the results in an empirically meaningful way. It's a good question. I mean, mapping out these sort of contagion effects is really tricky. There's actually a PNAS paper that Facebook participated in and generated quite a lot of controversy. And they end up finding that there are these spillover effects, but they end up being like empirically small, which is consistent with what I see in my data. Good question.
Thank you.
Yeah, if you don't mind just letting me know when I get a QA. I am not sufficiently sophisticated to get the QA screen up right now. Also not sufficiently sophisticated to have put a button to get me back to where I started. Okay, so that's kind of how the tweets are processed for sentiment, and I'm happy to talk more about specific techniques here. Again, Vader is just sort of a more sophisticated version of what I showed you with the fin that deals more better with some of the nuances of text analysis. One of the nice things about these data, as I said, there's quite a lot of tweets. I have more than 1 billion tweets in my analysis data set. And if I map those out, you can see that this is not, there's no other information on here besides the border of the United States and the location of tweets. And the location of tweets pretty closely approximates the distribution of the population in the US. And you can even see that you can map out major highways. You can see bodies of water. You can see all of this sort of features of human geography right in the tweet data. So tweet volume is a logged measure, obviously. In terms of sentiment, average sentiment has clear and interesting spatial patterns. It's a bit hard to see here, but the southern United States tends to have lower average sentiment. The sort of middle west and the upper west has higher average sentiment. Urban areas tend to have higher average sentiment, and rural areas tend to have lower average sentiment. This is more like sort of facts of interest than anything that's going to impact the empirical analysis, because I control directly for these metro area fixed effects. So we're not going to be comparing, for example, Los Angeles to somewhere in Iowa directly. We're going to be using fixed effects to take out that unobservable variation and then compare Los Angeles to itself on different hotter and colder days. So to do that, the empirical specification that I use takes average sentiment in a metro area C on date D. So that's S, bar S underscore CD, as a function of temperature. That's the first term. And that term comes in flexibly. So I'm going to show it to you as bins, but I've also estimated it as splines. You can estimate it in a linear model. I don't think that makes quite as much sense. But quadratic does make some sense here. You can I include precipitation. I include fixed effects for each metro area. And then I have a range of time-related fixed effects. So these are going to be, these are going to be day of week, holiday, and then month of sample, and actually month of sample by state fixed effects to control for correlated trends across areas. So estimation is a pretty straightforward fixed effects model, but I want to come back to this idea that this is not a model you could possibly run with any of the traditional approaches to no market valuation. So it's important here to say that one of the main benefits of the Twitter data set and of the rich panel variation that I have is this massive kind of specificity in location and being able to build a panel that has both fine-grained temporal and fine-grained spatial variation. So what do I find? Well, across all of the measures that I have, I find a remarkably similar effect. So I see declines in average sentiment in every single measure in both cool temperatures and in warmer temperatures. There's some evidence that warmer temperatures have a steeper decline. Again, as you can see, this histogram shows you that most of the bulk of the temperature data sits around 20 to 30, 35 degrees Celsius. This is going to be maximum daily temperature. And of course, since we're thinking about a climate change context, what we're considering is what happens when this whole distribution shifts to the right. So we really are a little bit more concerned with what's happening on the right side of the graph. And what's happening on the right side of the graph is that sentiment seems to decline. So coming back to this question about what are people's preferences for ambient temperature, this is kind of the finding, right? People prefer temperatures between about 18 and the low 20s, and they just prefer temperatures that are much cooler or much warmer than that. So that's consistent, I think, with the lived experience. Actually, this paper was covered in a popular journal early on in its life, and the headline was "Science confirms the obvious," and this is kind of the case here. Science is confirming the obvious. Great question about selection bias, Mulu, and I will get back to that shortly because I think that's important. Okay, this regression is similar, except rather than looking at sentiment, now I'm looking at the change in the percent change in the number of profane tweets. So the left-hand side is the profanity metric that I told you about. This is a list of about 300 profanities that I found somewhere online. That was a fun day. And then on the right is just a particularly aggressive profanity that I added as a robustness check. And you can see in both of these that we get pretty dramatic changes in the percent of profane tweets that are being uttered in these hotter and colder temperatures. So consistent with what I find in the sentiment data, profanity rises in the tails. This is related, I think, to some of the crime literature, which suggests that we do see these increases in crime in both hot and cold weather. Sorry, we see increases in crime in hot weather, but not in cold weather. What's interesting here is that I see the same kind of aggression response increase in cooler weather, but maybe that didn't get translated through to crime just because there's an availability kind of filter in crime. So you need to be outside to commit a crime, but if it's very cold, maybe you're just like angry, but not committing crimes. That's speculation. I'll get to that question too. Good question, Juri. Okay, so just to circle back to the kind of motivation, can we actually use this to value preferences for temperature? Because one of the big benefits of the hedonic approaches and some of the other approaches is the valuation piece. The valuation piece, you can actually value the degree to which people prefer one thing over another. So in the paper, and you know, I encourage you to read the paper for more details, but the answer here I think is possibly. It requires some potentially courageous assumptions to do so. So I have two methods that I propose. They find similar qualitative results, but you know, different by a factor of 2. So I think there's definitely more work to be done to really nail this down. One is using a wage regression, which really just compares changes in wages to changes in sentiment and uses that as a denominator. And the other is more narrow. It looks exclusively at posters who document receiving a parking ticket and looks at their change in sentiment on subsequent days to generate a different denominator. There, like I said, this is a paper that is published, which means it went through lots of rounds of reviews, which means there are a lot of robustness checks in it. And you're welcome to read them all. Please do. They took me forever, but here are two that I think are particularly interesting and related to text analysis. One is this picking up weather-related crime or also mortality effects? And then 2 is like, what is the difference between these like geolocated tweets and non-geolocated tweets? So this gets at Mulu and Juri's questions, the second one. So first on crime, like I said, there's a well-documented effect of weather on crime. Maybe what's happening is expressed sentiment changes are just reflecting more crime, right? I'm like mad because I'm getting mugged or attacked, or like the increase in crime is just generating this change in sentiment. So one test we can do is to just exclude all tweets with crime-related words and see if this effect attenuates. The trick here is to choose words in a way that's sort of credible and isn't cooking the books in favor of the result that I want. So to me, the most straightforward approach to do this was actually to leverage what's called word embeddings or word vectors. And the idea behind a word vector I'll get to in detail a little bit later, but basically it's a way to deliver similar words to a starting word or set of words. So I start with the list of crimes in this previous paper, and then I add the top 50 closest, nearest in statistical sense, using this word embedding from the Stanford group, so it's called the club. I find that these are the set of words that that are related to my sort of initial seed set of words. So these all make sense for the most part. Yeah, it's a pretty intense set of words. But looking for those words, and then in this column, so this is a robustness check in the paper appendix. You can see that the effect in this third column, where I exclude no crime and also no mortality related words, drops the number of tweets in the sample by about 100,000. Sorry, by about 100 million, but it doesn't substantively change the point estimates. Also, ruling out, as I said earlier, the mentioned tweets actually increases the size of the point estimates. So that's one check that I thought might be relevant. The second one is whether or not these geolocated tweets are actually comparable to all tweets. So geolocated tweets are about 1 to 3%, depending on who you ask, of tweets. I ran an analysis where I collected, for a month, I collected a sample of all tweets, and within that, some set of geolocated tweets. I found that it was actually like 3 or 4%, which may just reflect that when I did this, which was in 2018 or 2019, more people were geolocating their tweets. There's a lot of different tests that you can do and that I did to compare the geolocated tweets to all tweets. So again, these came at the same time. So except for being geolocated versus not, they should be comparable. One I want to show you is that I was able to compare the lexicons between the two sets. And what you can see is that the people are generally using more or less the same words in both sets. So this is just the rank of tweets in the non-geolocated set in the first column, and then the rank of words in the geolocated set in the second column. And this is only over about a month, and the geolocated set is much smaller, as I said, but generally speaking, they seem to co-occur at the same frequency. So I run a bunch of other checks that suggest that the main difference between geolocated tweets and non-geolocated tweets is that the geolocated ones appear to be from more, quote, real people, because there are fewer observations with zero sentiment. So you get zero sentiment when you get kind of neutral tweets that might come from news sources or non-human actors. Okay, so predictably, I'm like running short on time for everything I want to say. But just to wrap this piece up, non-market evaluation typically is done with techniques that have difficulty accounting for unobserved, correlated, usually cross-sectional variation. To deal with this, I combine expressed sentiment from Twitter with fine-grained weather observations to estimate preference for temperature. And the rich spatial and temporal resolution of this data set lets me use fewer identification assumptions than the existing literature. Remarkably, I think, across every single measure of expressed sentiment that I tried, and I promise you I did not try more than these, it was more than enough work to set up the ones I did show you, I find the same upside-down U-shaped response. So I want to bridge from that, which is like a specific example of text analysis in a social science paper, to talk about Texas data more generally. So I should say I've borrowed both the title of this section and much of the content, frankly, from a great JEL paper that came out last year or a year ago by Genskow Shapiro, Matt Genskow, Jesse Shapiro, and Matt Taddy. And I'll cite them explicitly in a second. But let's just start by observing that like the amount of text data is dramatically changing. So starting from the most analog, if you look at the number of books according to Google Books, the number of books in the world produced each year, you can see that it hovers indistinguishably around zero for hundreds and hundreds of human history. And then we hit like 1980, 1990, and all of a sudden there's like tremendous exponential growth, hockey stick growth. It's not just books, of course. If we zoom into a more recent period, Twitter has experienced less dramatic, but quite dramatic growth over the course of its lifetime. So this is from 2010 to about 2018. That slide has the wrong title. And we've also seen that there's more and more and more tweets per day. So there's more and more text data coming available every day than there ever has been before in human history. And it's not just books and Twitter. Certainly books and Twitter are a big part of it, but you could also think about like congressional records are now available, and more of these sources are also being digitized, which is important. Newspaper, internet searches, voice transcriptions, emails to some degree, SMS and WhatsApp to some degree, I guess conditional on them being available publicly. Medical records are a really common source of text analysis data, and then websites and blogs and Wikipedia. So there's a tremendous amount of text available in the world now that wasn't available 10, 20, 30 years ago. And I think this presents like a really nice opportunity to start learning things that we might not otherwise be able to learn. So text data has been used in economics actually for a couple decades. It's been used in every single field. Here's a sampling of fields besides environment. I just showed you an environment paper, but finance, macro, IO and marketing. Actually, marketing was like the original source of sentiment analysis. It was when it was called opinion mining. And then political economy is like a classic setting for speech content analysis, which is really a form of text analysis. Using text in quantitative research is tricky because text is not structured data. Text is fundamentally unstructured data, or very, very loosely structured data. But to run a quantitative analysis, we need a data set. We need something we can throw into Stata or R, and we need to be able to like generate variables from that data set. So you can think about variables from text data as either the object of study or a proxy for something that we care about, or maybe the outcome of interest per se. So we're either going to be including it in a descriptive analysis or in a causal analysis, or we might be including it in a predictive analysis. In either case, we need to use some form of natural language processing to transform this unstructured text data into a structured set of quantitative variables that we can include in our models. So natural language processing, sorry, full disaster on presentation slides. Natural language processing is a huge range of techniques. Here are some, ranging kind of in increasing order of abstraction. So from least abstract to most abstract. You might think about word frequencies, TF-IDF, co-location or tagging is sort of very rough descriptions of whether words are in text and how they co-occur. Topic extraction is kind of a level up. What is this text about? Sentiment analysis is maybe another level up. What is the valence of this text? What is the emotional state? And then semantic analysis, summarization, translation, or text generation. These are much higher levels of abstraction than the other three. So to understand text as data, you need to understand that raw text is extremely high dimensional data. So for documents with like W words and P possible words, there are P to the W possible representations of each document. If you just restrict this to what you can put in a Twitter post, which is not most of the documents or sources of text data that I just mentioned, the number of possible Twitter posts exceeds the number of atoms in the universe. So I don't care how good your machine learning algorithm is, you cannot run regressions with raw text. To analyze text data, therefore, we must reduce this dimensionality somehow. And so this is where we're really going to follow Genskau, Shapiro, and Taddy. And the way they describe this is that there are basically three steps to any analysis involving text data. The first is we want to represent raw text as a numerical array C. So raw text D into a numerical array C. Second step, we want to map C into some predicted values V of unknown outcomes. So the predicted values represent the unknown outcomes. Then we use hat V in subsequent descriptive or causal analysis. So descriptive here could include a predictive analysis. I know I'm running a little short on time, so maybe I'll just, the slides will be available, but I'll stay at kind of at high level. What do you think, Lulu?
Well, you have 10, 15 minutes, feel free.
Okay, never mind. I'll just keep talking. Feel free to interrupt with questions. Okay, so the idea in step one is that we want to take our raw text and we want to convert it into some form of numeric data. And that means that we need to split our text, first of all, into documents. So you want to ask, what is the right sort of aggregation of documents here, right? And the way you want to answer this question is by thinking about what you're eventually going to compare that text data to. So if you have, let's say, unemployment measures for counties on a quarterly basis, you're going to need to aggregate your text data in such a way that it's going to match that county by quarterly data. So you can split it up into individual documents, and you can sum. But at any rate, you're going to need to combine your text into some aggregation that will match into the one you'll eventually use in your analysis. Usually individual documents, let's say, legal briefs or newspaper articles or tweets, usually we'll treat those as independent. And again, this is purely for computational reasons. This thing like spins out of control in a dimensionality sense very, very quickly if you don't apply some structure. On the topic of applying some structure, then you need to choose your features. So this is when you're really getting from D to C. And by choosing features, you're going to be able to take just this like unstructured raw text into a matrix format, into a data format. Usually people will do this by first removing words that don't have much meaning. That can either be a word that's extremely common. So like the word "the" is not particularly valuable for most text as data exercises because it appears so frequently and doesn't tell us much about the underlying text. Or words that are very rare, right? So if you have a word that appears a single time in all of your corpus, that's all of your documents, then it's not going to be very useful for generating variables because, I mean, imagine like a dummy variable that's exactly once in your data set. So that's where TF-IDF comes in. I'll just let you Google that if you don't know what it is, but it's a technique to do exactly this. Then you need to choose, okay, am I going to use unigrams or bigrams or n-grams? And that's really just like, am I going to take each word in this document as separate? Or am I going to like combine them somehow? So I like look at two words together and count that as a feature. Usually, I mentioned stemming earlier, usually part of this process will involve stemming. So rather than looking at like running, runner, ran, all these different words that are maybe like different verb forms of the same word, or one's a gerund, you collapse that all into run. And then maybe you remove punctuation numbers and URL. So again, none of this is required, but you have to collapse your dimensionality somehow, and choosing features is kind of one way to do it. So just to give you an example of feature selection, and again, this is from the nice GAO paper. Good night, parting is such sweet sorrow. From Romeo and Juliet. After removing stop words and stemming and punctuation, what we would be left with would be just good night, part, sweet sorrow. All right, so you can see where the stemming has happened on parting. I shouldn't have left that period there because I said I removed punctuation, but you get the idea. And so what's called a very typical approach here is what's called a bag of words approach. And so a bag of words approach just counts the number of words in this document of each type. So the count for good and night would be 2, and then 1 for part, sweet, and sorrow. You might extend that to bigrams. So then you would also have good night with a count of 2, and then 1 for night good, night part, sweet, sweet sorrow. You can extend this further for additional numbers of n-grams, but the dimensionality increases really, really quickly, especially with longer documents. Usually people stop at around 2 or 3, or even at 1. Okay, so now you have a data set, and you want to map that data set to your predicted values v. At this point, you're in whatever model you're used to, right? This could be like a regression, this could be a neural network, this could be a regression tree, any of this stuff, it's just data. So you're now going to use whatever model you want to use to connect the features that you generated in step 1 to the attributes that you carry in V. Examples of this include identifying spam, predicting sentiment, identifying clue clusters, that sort of thing. There's a couple different ways that you might do this, and I guess this gets back a little bit to step 1, but the mappings that you take from the features to C basically take 2 forms. So they could be dictionary based, or they could be more statistical approaches. So what I showed you in the paper that I talked about was a dictionary set of mostly dictionary based methods. These methods don't involve statistical inference, at least not in the direct process. The idea here is that we're gonna just use some function of C that we've generated that maps counts of words to some vector. So the idea here is that this is another layer of dimensionality reduction. And in the case of like this Greenstone and Hanna paper that looks at whether or not a newspaper is talking about air pollution or water pollution, it might just be a pure word presence test. So what they're going to do is they're going to say, okay, we're going to generate an indicator, that tags every newspaper article with the words air pollution or water pollution in it as indicative of environmental interest in this article. That's probably the most rudimentary way to map from words to a numeric value of interest. Sentiment analysis may be one level down, and again, this we've already talked about, but it's mapping like hate to some number with a negative valence. Here, -3, love to 4. And so all the function is doing is just saying, okay, I have a score for each one of these words. I'm going to apply that score. You can generate dictionaries in lots of ways. Most of the time they're sort of ad hoc, but you can have rule-based dictionaries. They might involve some sort of in-depth analysis on the back end, some kind of statistical analysis to generate the dictionaries themselves. Statistical methods are a little bit more nuanced, and the idea here is that we want to estimate the probability of observing kind of a true VI. So let's say that VI here is sentiment, conditional on the words that we see. So the approach is going to be a little bit more natural if the end goal is actually just to predict the underlying VI. And many of our like usual machine learning ideas might apply here, right? If you're facing a high dimensionality of words, let's say you just like included unigrams and bigrams and trigrams, you're going to be inclined to use like a ridge regression or a lasso or something that will select features for you. Alternatively, if you're interested in the probability of observing a given set of words conditional on an outcome, which might map structurally better into your data generating process, then you're going to build what's called the generative model. And these are more likely to be like kind of a neural network approach where you're identifying the latent attributes of a text, such as topic or political bias. So practically speaking, thoughts on using these methods. I think it makes a lot of sense to examine, if you're using a dictionary method, to examine the dictionary and understand how it interacts with your research question. So one that was relevant for me was if you're writing a paper on the weather's effect on emotional state, on sentiment, you don't want to code tweets that include the word sunny as a positive. So you want to just like take sunny out of your dictionary or just throw out those tweets entirely. Dictionary methods are really useful when the mapping from the dictionary to the object of the interest is intuitive and makes sense to your reader. If that mapping doesn't make sense, or if it's sort of too far-fetched in a constructability sense, then the paper probably doesn't make sense. Text regression is more useful when you're predicting a single attribute when you have lots and lots of labeled data. So that's like the emoticon example I gave. If you have lots of attributes of interest or not very much labeled data, then it can be more useful to use generative models. If you're interested in more complex feature sets, neural networks, and in particular word embeddings, are quite interesting, especially if you don't have don't have the ability to reduce dimensionality in other ways. So word embeddings, just very briefly, again, borrowing from this paper, word embeddings are basically a way of representing text as a much more limited dimensional vector. So in this case, this is not quite how these work. They're usually more than 2 dimensions, but let's say that we can map these words into 2 dimensions exactly. Child, man, and woman would be vectors that were very close to each other, whereas king, queen, and prince would be close to each other as well. So if you think about the crime-related words exercise, maybe I started with queen, and then I would get king and prince in my set because they're close in terms of raw distance. Word vectors actually have another really nice feature, which is that you can add and subtract them in ways that make some logical sense. So if you start with king, subtract man, and add woman, you end up quite near queen, which should make intuitive sense. The last step is that you want to use hat V in your predictive and causal analysis, and how you're going to use this and present this varies a lot by setting. Often hat V is the outcome of interest. So if we're doing a predictive model, maybe we want to know how do we predict this thing we're interested in using text. So this is where the machine learning work you've been discussing really makes sense, where you take this text data, maybe you collapse it to word vectors, or you collapse it to embeddings, or you collect it just to a set of dummy variables on words. And then you see if you can use those variables to predict something you really care about, like unemployment, as Scott and Varian do just with search data. Alternatively, maybe V hat represents something that we care about but can't otherwise observe, and we want to see the effect of other stuff on that. So Hayes, River, and Schifale look at how and whether pollution makes politicians dumb. Their outcome of interest is the complexity of politicians' speech. So that's their V hat. Paper I just showed you takes expressed outcome as the outcome of interest. Finally, V hat might be an important explanatory variable that we don't otherwise get to observe. So I think this paper is pretty well known. The effect of racial animus on the 2008 USA election. Steven Zavitowicz actually measures racial animus using data from web searches. So that's, sorry for running all the way basically to the end of time, but that's sort of what I have to say about text data. I very much recommend you checking out the Getska, Shapiro, and Taddy Texas data paper. The closing thoughts that I have here are that in principle, text is not fundamentally different from any other source. In practice, you can't possibly include text data, raw text data in your models, or if you can, tell me how. So you have to make some decisions around collapsing dimensionality. My suggestion with respect to that is you need to compare samples of your data in terms of raw text to what you get in C, so your variable vectors, and to what you get in V hat, which is your predicted values. You want to make sure those make intuitive sense, especially in projects where they represent like a causal impact. You need to be transparent about these design decisions because you're going to be making a lot of them, and many of them won't be trivial. And then finally, I'm happy to talk offline about choice of tools, especially in projects with many documents. The choice of tools matters tremendously with how quickly you're going to be able to move through your project. So that's all I have to say. This is my email. I guess I should have included my Twitter. It's Baylis. Thanks for your time.
Thank you very much, Patrick. And one small question. Actually, this is my question. And I guess you are using panel data, if my understanding is correct. And because you are using only geolocated qubits, and do you have any the limits in the number of qubits in that small cells, and in any given region, any given day, if you have few qubits and you skip it, or just I mean, if you have, for example, we have been Juri also working on the same kind of tweet data, so that's why it's interesting for me. Our idea is if we have few tweets in any given time and given location, and it is difficult to have a kind of any type of sentiment So that's why it's just, for example, we are working in the chronic disease surveillance systems, and that's basically, we have sometimes 40 TBits in a given time. And then do you have any idea on that, the number of restrictions on the number of tweets and to get any meaningful results?
Yeah, I mean, I found that if I don't include weights of some sort, usually just like the number of tweets on average in that cell, so in this case, in the metro area, you get a lot of nonsensical results because, yeah, when you take this average and there's only one observation contributing to the average, this is a noisy process and it tends to be, those tend to be not like very representative cells. So one way is just to weight by the number of observations represented by that average. A second way that I found is useful is just to like restrict the sample to, you know, cells where you observe greater than 100 tweets, in my case, greater than 100 tweets on average for the course of the data. Those approaches, predictably, I think, deliver more or less the same answer in what I found.
Yeah, thank you, great.
Is it possible to close sharing screen options?
Oh yeah, stop.
All optimized.
And right now, the attendees are able to see us, I guess. Yeah, so right now, everybody is able to see us. That's nice, nice closing picture. And we see each other. It's not weird anymore that you are speaking to yourself anymore. Okay, thank you very much, everybody. I mean, all the panelists, and it was a great 2 day, and they just, we appreciate your time and effort, and then I hope all the attendees and benefited a lot. And we had also 3 days summer school, and then all the things that the talks that you did and were related are related to what we did in the 3 day summer school. And again, thank you very much.
Thanks, everyone.
Thank you.
Thank you very much.
Thank you.
Bye bye. Bye.
Bye, everybody.
Bye bye.